Okay. Let's consider predicting a value of y at x, but doing it in an inferential way, not just giving a prediction. You already know how to get a prediction. So, as example, from the two examples we've covered, we might want to predict the price of a diamond given the mass, or we might want to predict the height of the child given the height of the parents. So the obvious estimate for a prediction at a point x naught, we've already talked about this, is just beta naught hat plus beta 1 hat x naught. But if you actually want a prediction interval, right, something that incorporates the uncertainty associated with that interval, you need a standard error, okay, and some knowledge of what the distribution of the prediction estimate is to create an interval. There's a kind of subtle distinction between, I guess what I would say, intervals for the regression line at point x naught and a prediction of what a y would be at point x naught. And I think a picture will help describe this. So at any rate, for the line, we get this standard error right, or this standard error right there. And you can plug directly into it. And for the prediction interval, you get this standard error. And the only thing different, right, is that 1 right there. So you get a wider interval for the prediction interval. So let's see what it does. We'll go through our code, and then we'll see what it does, and I think you'll understand it better. So here I'm generating a plot of my x and y's, and I have all my my little settings I like there. I'm going to add a fitted regression line. Here's my x values that I want to predict at, and my y values that are my predictions, beta naught plus beta 1. Or remember, I defined beta naught and beta 1 previously. So those are the coefficient values. I'm giving my two standard errors, and then I'm going to plot my lines. Notice what I did when I did this, the collection of values I wanted to predict at. It's a dense grid from between the minimum observed mass and the maximum observed mass. So I'm plotting the prediction lines on prediction estimates on a very fine scale, and then I'm going to plot all these lines. The plus two, and I'm being lazy. I should use the appropriate t quantile, but I'm just putting 2 in there because for a Gaussian, the 97.5th quantile is 1.96. That's around 2. The t quantile should be a little bit larger. So I'm being lazy. I should put in there qt, right, 0.975, and the appropriate degrees of freedom is n-2. Right, I should do that, but I didn't do that. And in fact, it didn't save any time because I just spent all this time describing it. So one thing to notice, the width of the prediction interval, right, it's not constant, right? It's gonna, let's see, if you look at it, right, look at the prediction interval width here, or I'm sorry, the regression line interval width here and the prediction interval width there. That function is going to be lowest when the x values are at or near the mean, right? Because this term right here is just going to drop out, right? So your prediction interval is going to be narrowest at the mean, and it's going to increase as you go away from the mean, right? So that's exactly what we see. It's a little bit hard to see on this picture. It's maybe easier to see on the regression line picture. But if we were to say, which makes total sense, but if we were to say predict a point way out here where we haven't observed any data, the prediction lines bow out a lot more. Okay, so here's the difference between predicting the regression line at that point and versus the prediction interval at that point. See how well these points generally fall on the line. We're pretty confident we have the line, right? Maybe not perfectly, but we have it pretty well, right? I mean, those points fall pretty well on that line. So we know we've got the line really well estimated. Okay? So if what we wanted to estimate is what is the value of that line at that particular point, right? We don't actually have a lot of uncertainty, right? We may have messed up the line by a little bit, but not by much. Not by much, right? And you can think as you get more and more data points, we're going to get a better and better estimate of that line, right? And so the variability associated with the prediction should decrease, right? And if you look at our formula, right, what happens? Well, you have this term that's going to tell us, well, if you're far away from the average of the x's, you're going to have a little bit worse prediction. But then there's this other term, right, 1 over n. As we get more and more data, right, that goes to 0. Right, that goes to 0. So if we're predicting at the average, right, as we collect more and more data, that interval is going to go to 0. In contrast, look at the prediction interval. It has this part 1 that doesn't decrease with n, that's just intrinsic, that never goes away, right? And that's, so the prediction interval is these lines right here. So if instead of saying, what's the line at 0.3, I want to say, I want to guess what a particular y value is at 0.3, well, then you have to include all this uncertainty for the points around the line. If we collect an infinite amount of data, that's not going to change the amount of variation in these points. The infinite amount of data is going to change the amount of variation in how good the estimate is of the line itself. And as we're saying, if we want to predict the point at a line, then we're going to do quite well and the interval goes to 0. But if we don't, right, if we want to predict the point, well, then we have to incorporate the uncertainty associated with all the points around the line. And you can see these prediction lines for the prediction interval, not the expected value at a point x interval. They kind of encompass the variability of the points themselves. So most of the points kind of lie close enough lie within the prediction interval. So that prediction interval incorporates that uncertainty of the points around the line, whereas the prediction for the line at that specific point only is concerned with how well have we estimated that line. And so for the prediction interval, another way to think about it, right? For the prediction interval, there's three parts, right? There's sort of like this part that says, well, how close to the average are we relative to the variability of the x's? That kind of talks about how close to the middle of the data you are where you should get good prediction, right? This part kind of is added on, sort of relates to how good is our estimate of the line, right? So both these parts, both those parts go to 0 as, both these parts go to 0 as you collect an infinite amount of data. And then there's this part right here, the 1, that just never goes away as you collect more and more data, and that just says how much variability is there around the line. And I just to reiterate, that makes a lot of sense. If our regression points fall, like with this amount of variability, right, around the line, right, it makes sense that if we collect, let's say we collect 100 billion data points, well, we should get that line pretty well, right? We should get that line pretty well. But what we'll never get rid of is the fact that the points fall randomly around the line, so that if we want to incorporate that uncertainty into our prediction, we use one interval, or if we just want to predict what's the line at that specific value, then we use a different interval. So to me, it makes a lot of sense, and that's why there's two different intervals. Okay, so just to discuss these points on the slides. So both intervals have varying widths depending on how close to the center of the data you are relative to the variability of the data, the x's. So in our specific case, we're quite confident in the regression line, so that interval is very narrow. And in fact, another way to think about it is if we actually knew beta naught and beta 1, this interval would have 0 width, right? We would know exactly what it is. However, the prediction interval must incorporate the variability in the data around the line. So even if we knew beta naught and beta 1, that interval would still have width, just the residual variance around the line. Okay, so that's why we get two different lines. So how do we do this in R without having to actually manually do the predictions? There's this nice function predict, and you guys are all hackers. You should be able to figure out how to use it. You have to define new data. It has to be in a data frame, and your definition of your interval will tell you the width of the interval and so on, which are the two kinds of intervals it does. And here you can see just I did it, and you get the same picture. One last thing I want to point about standard errors that I maybe forgot to point out earlier is the slope standard error, right? The standard error for the slope. I should have pointed out this earlier. When is this variance of beta 1 the lowest? Well, you want variability in your x's, right? That's an important fact. I want to make sure we emphasize that. You want variability in your x's because it decreases your variability in your slope, right? And that makes a lot of sense. How well are you going to be able to estimate a regression slope if you collect data all right in a little cluster, right? Very little variability in my x's, there's going to be a lot of variability in my regression slope, okay? But on the other hand, if I collect data nice and spread out, right, then I'm going to get a better estimate of my regression slope. And it turns out the maximum amount of variability that you can get, by the way, is the following. Take half your points and put them very low, and half your points and put them very high. And as much separation as you can get in these two things, and you want these to be all even at the same point, as much separation as you can get in those, then the better your line estimate is. Now, I'm wondering if anyone can see the problem with that strategy if you were to, say, design data collection. Well, ultimately the problem with that strategy is you got to be very certain that this linear relationship holds between your two sets of points, right? You're quite confident at your average y value there, and you're quite confident at your average y value there because you collected a lot of data at both those points. But if the relationship is something like that in between, then you've totally messed it up. And not only have you messed it up, but you haven't collected any data to evaluate that problem, right? Residual plot would show nothing, right? You've only collected two different values of the x's. But at any rate, so I think people intuitively, if they were to design an experiment, wouldn't dump all their data at one point and at another x point like that unless they were quite sure of the linear relationship. People wouldn't do that intuitively. But what's more important is just this idea that if you want to investigate regression relationships, what's important is to have lots of variability in your x's and little variability in your y's. That's the ideal circumstance, right? What's the best circumstance? You have all your data points falling on a nice line or close to a nice line, and your x is nice and variable. That's the best point. And that's when we think of a regression, like a really nice regression data set. That's what it looks like, right? The x variation relative to the residual variation, relative to the x variation is being very small. And that's what we think of when we think of a great sort of very nicely fitting regression line that should be well estimated. And I think the diamond example is an example that looks pretty much like that. To me, that's what hopefully I don't know a lot about diamonds, so I don't know if this range of carats is the right, is a good amount of variability in the x's, but there isn't that much residual variability. So it looks like a nice regression relationship, and that's what it's saying. So it is nice that all of our formulas exactly mirror our intuition.